Good afternoon, everyone, and welcome to this Aalto Physics Colloquium event that has today a very distinguished lecturer, Nobel Prize Laureate from 2014, Professor Hiroshi Amano, who is going to tell us about how to illuminate the world with LEDs. Of course, I wish to welcome Professor Amano as well very much to Aalto University today. Just a few quick notes about this event. So, of course, we are now in the International Year of Light, so it is very appropriate to discuss illuminating the world. Also, this event being part of the Aalto Physics Colloquium series, we're also extending the annual meeting of the Finnish Physical Society in a sense today, that because this meeting ended today at around noon, it's a continuation of many good traditions. But my job is not to be speaking for very long today, so I will leave the floor to Professor Amano. Please, the floor is yours.
Thank you, Rip. Good afternoon, everyone. It's my great honor to be here and give a talk on the history of the development of blue LEDs. But before explaining the blue LEDs, so some people are very young, so I'd like to explain first. What's happened if you become Nobel Laureates in future, okay? I had experienced plenty of unexpected things during the Nobel week, so maybe I should be responsible for explaining what's happened, okay. There was an announcement on October 7th, but at that time I was in a plane and there was no information. So when I got off from the plane at Banquet and opened the PCs, I found plenty of emails entitled "Congratulations" or the "Omedetou gozaimasu" in Japanese. But since I didn't see the contents of the emails, so I thought it was some kind of spam mails sent across the PCs, and then went to the real final destination and found several Japanese-like journalists waiting for someone at the arrival gate. So I recognized that someone got the Nobel Prize. Maybe my teacher, Professor Akasaki, got the Nobel Prize. But when I went through the plenty of journalists, someone told me that, Amano-san, do you know what's happened? You got the Nobel Prize. Oh, what happened? That's the story. So I didn't get a phone call from the Nobel Foundation. We went to the Good Nobel, and I got plenty of interviews from the TV teams and also the newspaper teams. And from October 7th to December 23rd, there are plenty of requests for interviews because the last year there are 3 Nobel Laureates in physics, the Professor Akasaki and Professor Nakamura and me. Professor Akasaki and Nakamura, Professor Nakamura is very famous, so they were the candidates for a long time, more than 10 years. So the journalists knew them very well, but no journalists know me. So maybe I'm so interested to them. So during this period, there are more than 200 requests for interviews. But this year, the number is increasing a lot. More than 200 requests for lectures this year. In Japan, if the people get the Nobel Prize, it automatically get the Order of Cultural Merit from the Emperor of Japan at November 3rd. So I received this medal from the Emperor. And there are several TV programs. The NHK is Japanese national TV systems. There is an interview of Science Zero, Science View. This is the TV program. And from December 6th, the Nobel Week starts. Okay. This is the photo from inside the Nobel Museum to the outside. Last year, more than 150 journalists gathered to the Stockholm, among which the journalists from Japan is more than 100. So 2/3 of the journalists were from Japan. Okay. And I was so surprised that there is the court attaché. In my case, Miss Anki support us everything during the stay at Stockholm. So the attaché's family and my family enjoyed a dinner on December 6th. Then on December 7th, there is a joint press conference at Stockholm University. Unfortunately, Professor Akasaki could not join this conference. So Professor Nakamura, I, and the laureates of chemistry and economy did the interviews. But I'm not so familiar in explaining in English, so I was so nervous at that time. Then there is another interviews by Japanese media. So this was on December 6th and December 7th. And then on December 8th, there was a Nobel lecture. So more than 1,000 people gathered, and the laureates in physics enjoyed the lecture in the morning, okay, in the morning. And then at lunch, there is a celebration ceremony supported by the embassy of Japan in Stockholm. So we enjoyed the drinking, especially the alcohol, beer, and wines. Okay? Then in the evening, there is another big event that was Nobel concert on December 8th. So there is a very traditional and very big halls, and the royal family sits just at the center of the second floor. And the Professor Nakamura's families are there, and my families are there. And the soprano and trumpet, the music I heard that the music was very nice. Okay, once again, I'd like to explain. Nobel lecture in the morning, and we got a lot of alcohol in the lunch. And the music was very nice. So I fell asleep. Yeah, I heard that the music itself is very, very nice. And December 9th, we visited the science high school at Sister. And in this visiting, first I enjoyed to see what the schoolboys are doing. But suddenly the teacher asked me to do some classes to teach something. So I was so amazed. I didn't prepare anything. So I became so nervous, but I explained how to continue the research or something. And then we visited Ericsson, one of the very famous communication companies. And we are so surprised that from Sister to Stockholm, it's about 30 minutes by train. But all the trains were chartered or reserved. So only 2 persons, President Nakamura and I, enjoyed the train trip from Sister to Stockholm. Then after that, President Akasaki and I visited the Nobel Museum once again. And maybe you know that we signed just at the back side of the chair. So if you visit the Nobel Museum, you can find these chairs. And then on December 10th, there is the award ceremony. In the morning, there is a rehearsal. So we knew everything, okay, for the ceremony, how to proceed. But when the real award ceremony comes, all the roads are closed for us and take us from the hotel to the ceremony buildings. And we, all three, becomes very, very nervous. And we forgot everything for the procedure. But anyway, we could receive the medals and the diploma. And in the evening, there was a banquet sponsored by Royal Swedish Academy of Science. More than 1,300 guests are gathered, and royal family and Nobel laureates sit here and enjoyed the dinner. It's very nice. And after that, there is the party organized by the student union until in the morning, the 4 o'clock. Okay. So I was so tired and go back before ending up the student nightcap party. And then we visited the Nobel Foundation to get the medal and their diploma. And at lunch, we enjoyed the Japanese food, quite well. And on the afternoon of December 11th, there's a TV program, the BBC Nobel Minds. On December 11th, there is a banquet sponsored by the royal family. Of course, the photo is prohibited. So I prepared the different photos. Okay. On December 10th, I sit just beside the Queen Sylvia, and on December 11th, I sit just beside the Princess Victoria. So we enjoyed the discussion for the education in Sweden. Yeah, she said that previously the level of the education in Finland and Sweden is almost the same. But now the Finland education becomes much, much higher than the Sweden. So she complains about that. On December 12th, it's a final date of the official events organized by the Nobel Foundation. So I visited the Sweden Energy Agency to discuss with the LED lighting system at home. And then also I visited the Nora Real High School and enjoyed the discussion with the high school students. And also there is a reception by the Nobel Foundation. This is the final date of the event. So Mr. Satyarthi, he won the Nobel Prize in Peace. And the ceremony was done at Oslo in Norway. So unfortunately, the Miss Marara, the another Nobel Laureate in Peace, couldn't join us. But he can join us and enjoy the last reception. So then all the events, or official events, finished. Then we enjoyed the walking at the market, and I enjoyed the meals. I did not know that the people in Scandinavia eat reindeer and also the elk. People in Japan never eat that. So I was so amazed but enjoyed the meal very much. Then on December 13th, I visited Uppsala University. Maybe some scientists fields people know the name Angstrom. The Angstrom graduated this university. The building is very traditional, and I enjoyed the lecture at this atmosphere. And also, there is this festival is famous in Finland also? Oh, really? I was so surprised that this girl put the real candles on the head. Is it similar in Finland? Oh, really? I heard that there are some troubles. Well, the hair is burning or something. No? But I suggested to use the LEDs from next time. Okay. On December 14th, I visited the Lund University and enjoyed the discussion with the students in Lund University. Okay, so that's the all for the report of Nobel weeks. Then I explained the history of the development of blue LEDs from now on. First, I'd like to emphasize to the young people that the reason why you can enjoy the full color portable games or full color smartphones is because of the emergence of blue LEDs. Okay? This is the development of the LEDs performance reported by Dr. Haidt, the retired American scientist. The flux per chips increase 20 times per decade. And it started from 1962. The red LEDs developed by Professor Holonek. And 9 years later, Professor Banquet, another American scientist, developed the first gallium nitride blue LEDs. Okay? But as concerns the history of LEDs, before the Professor Holonek, the Dr. Grimmeiss, the German scientist, already published the red LEDs based on gallium phosphide in 1961. He was the real inventor for the LEDs. He already published in 1959 the luminescence from gallium nitride. Okay? And I met with him. He is already 95 years old, but he is very active still now. And when I visited the Lund University, I met with him. When I was a student, I read his paper plenty of times. So I enjoyed the discussion with Professor Grimmeiss. Okay. So I'd like to explain my history. The Professor Akasaki, my teacher, started the nitride growth. This is aluminum nitride from 1967. And in 1975, he started the gallium nitride growth. And then his group succeeded in fabricating Banquet type LEDs in 1978. But unfortunately, the Matsushita Research Institute, now Panasonic, it's Japanese very famous company, quit the development of blue LEDs in 1979. So he have to move from the company to Nakamura University in 1981. And then he started the nitride research once again at Nakamura University. And then I joined the next year as the undergraduate student. The dissertation research subject, nitride-based blue LEDs, is so fascinating to me because in 1975, the Bill Gates and Paul Allen developed or established a Microsoft. And in 1976, Stephen Jobs and Stephen Wozniak developed first Apple I computer. And then the development of computer system, especially the personal computer system, become very, very rapidly. So I want to contribute to the development of the computer or personal computer systems. But unfortunately, at that time, there is no laboratory at which the people can concentrate on the development of the computer system. But when I found this subject, I thought that one, at that time, the size of the display system based on the brown tube was too big. So if I achieved blue LEDs, I knew that red LEDs and green LEDs have been already commercialized. So if I can succeed in developing blue LEDs, I can change the world. That's why I was so interested in this subject. And of course, I know nothing about the difficulty of fabricating blue LEDs. One of the reasons why blue LEDs are so difficult to achieve is we use the gallium nitride crystals, okay? But if we synthesize the gallium nitride by the direct reaction of gallium and the nitrogen, we need a very high pressure and a very high temperature. So it is almost impossible to achieve. So we need to use the chemical reaction to reduce the temperature and to reduce the pressure, okay? So we use the ammonia as the nitrogen source, but the activity or reactivity of ammonia is very, very high at high temperature. So the materials which we can use as the substrate for crystal growth is quite limited. Among many candidates, the sapphire is most promising candidate because it was tolerant at high temperature and the ammonia atmosphere. But the problem is the lattice mismatch. That is the difference of the arrangement of atom of sapphire and gallium nitride. In general, if the lattice mismatch is less than 1%, it might be possible to grow high quality crystals. But if the lattice mismatch is higher than 1%, it is almost impossible to grow high quality material, okay? In addition, Professor Banquet developed the first blue LEDs based on gallium nitride in 1971. But at that time, they could grow negatively charged N-type gallium nitride, but they couldn't grow positively charged P-type gallium nitride. So the efficiency was limited to be very low. In addition, the responsivity or sensitivity of the human eye in the blue region is very low, only 3% compared with the yellow-green light. Okay? So that's why the blue LEDs are so difficult to achieve. So the students of the Akasaki laboratory started to investigate the blue LEDs based on nitrides. But the problem is in the early 80s, the funding situation of the university in Japan is so poor, okay? It's only 3 million Japanese yen, meaning how much? 30,000, or no, 20,000 or 30,000 euro per year, okay? In order to buy reactors we need at least 100,000, no. 1 million euros, okay? So no company can support us because of the lack of funding. So we have to develop the reactors for crystal growth by ourselves, okay? So we managed to develop the MOCVD system by ourselves, then try to grow the gallium nitride. I started the nitride research from the undergraduate 4th grade to master courses, 2 years of master courses. So I have tried more than 2 years. The experiments more than 1,500 times without any success. The large lattice mismatch of 16% is too difficult to overcome for the young student like me. And then, just at the end of the master courses, the other students found their jobs, but I decided to start the PhD from the next April. So I continued the very, very lonely experiments by myself. One of the 1 year elder students, Dr. Koide and I grew the nitrides. He grew the aluminum nitride, and I grew gallium nitride. And if we compare the surface morphologies of these crystals, his crystals' surface morphology seems to be better than my gallium nitride. So I decided to use the aluminum nitride just before the growth of gallium nitride. But I also knew that in order to grow high-quality aluminum nitride, we need temperatures higher than 1,200 centigrade, even higher than gallium nitride growth. But our system, heating system, is very old. Just built at 1960s. So I couldn't operate the heating system to temperatures higher than 1,000 centigrade. But just at that time, I remember there's some discussions with the young staff. The lecturer, Dr. Sawaki, explained to us that in case of the another materials, that is the boron phosphide growth on silicon, the lattice mismatch of which is also the 16%. Before the growth of boron phosphide, the supply of phosphorus, just before the growth of boron phosphide, he can grow the flat surface boron phosphide. And he claimed that phosphorus clusters should act as the nucleation center for the growth of boron phosphide. Then he can grow the boron phosphide with flat surface. Then I decide to deposit aluminum nitride at low temperature. So I thought that it should act as the nucleation center for the gallium nitride growth. When I took the sample out from the reactor, I was so surprised that, oh, I forget to supply the gallium source. But when I checked the reactor, I found that everything was operated properly. Then I checked the microscope and found that we finally realized the high quality or optically flat or atomically flat gallium nitride. So I was so excited and brought the sample to the Professor Akasaki. I thought that he was also excited, but he was very, very cool and suggested me to characterize the another properties because the surface morphology itself is not sufficient for using as blue LEDs. The another properties are also very, very important. So I checked the another properties like crystalline quality, electrical properties, optical properties, everything. And I found that every properties were far superior to the previous reports. And then I published the result to Applied Physics letter in 1 year later. So it took 1 year to check all the properties of the crystalline quality. So this technology is called the low temperature buffer layer and have been used worldwide. Okay, I should comment on the patent issues. Okay, there were the similar reports for the low temperature buffer layer. In case of gallium arsenide on silicon, there's already a report in 1984 using in this case, the low temperature gallium arsenide buffer layer, okay, from Oki Electric companies. And in case of the Professor Yoshida, he used the single crystalline aluminum nitride buffer layers in 1983. Okay, so I wrote the patents. Sorry for written in Japanese, but we concentrated on the patents just for the low temperature aluminum nitride buffer layers. Okay, but in 1991, another groups, the Japanese group, it is the Nichiya Corporation, the Professor Nakamura's team submitted the patents claiming that they used the low temperature gallium aluminum nitride buffer layer. But please be careful on this note, except only for aluminum nitride, okay? They claimed the gallium aluminum nitride buffer layer, low temperature buffer layer without aluminum nitride. Okay. So anyway, we realized the high-quality gallium nitride crystals. So the next subject is to realize the P-type gallium nitride. So from 1985 till 1988, I grew plenty of gallium nitride crystals doped with zinc, but all the samples shows highly resistive or N-type, no P-type conduction. But when I checked the luminescence properties, I found that the very sharp excitonic emission at low temperature. And I also found that the energy position or peak position changes according to the strain of the crystals. So I thought it was so exciting results and try to present at the Japan Society for Applied Physics meeting, annual meeting held in Nagoya in 1987. But when I entered the room, I was so surprised that there were only 4 persons in the room. Professor Akasaki, chairman, I, and another person. So only 1 person listened to my talk. At that time, there many people are interested in the another materials like zinc selenide or zinc sulfide. And the gallium nitride researchers are very, very minority. Anyway, I found another interesting phenomenon that during the electron beam irradiation, the blue luminescence of the zinc-doped gallium nitride was enhanced irreversibly. But so we call it the low-energy electron beam irradiation or LEAP treatment for short. But even after the LEAP treatment, the sample shows highly resistive. But in 1989, I became the research associate of the Professor Akasaki's laboratory and found that in the textbook, Bonds and Bonds in Semiconductors, written by J.C. Phillips, that this graph is very, very appealing, showing that in case of gallium phosphide, compared with zinc, the magnesium is much, much better in terms of the acceptor activation. But the problem is the cost of the magnesium source. At that time, the magnesium source gas cost is how much? 5,000 euro, which is too expensive for the young research associate like me. So I begged the Professor Akasaki to buy some, and he agreed to buy it. Then, after several months later, the master course student and I tried to grow magnesium-doped gallium nitride. As for the magnesium doping, we are not the first one. Dr. Maruska, at that time, the student of Stanford University, already published mistype blue LEDs or violet LEDs using the magnesium-doped gallium nitride. And as grown, magnesium-doped gallium nitride shows highly resistive, but after the LEAP treatment, all the samples shows P-type conductions, and we succeeded in fabricating P-type gallium nitride and also the PN junction LED for the first time. And then in 1992, the Professor Nakamura's team, the Nichia Corporation, found that even the thermal annealing, we can fabricate or we can grow the p-type gallium nitride. And then they submitted the patent in 1991 for the thermal annealing. Okay. The mechanism was already known that it was hydrogen passivation, first explained by Professor Van Bechten. He passed away last year. And by the Levy treatment or by thermal annealing, the hydrogen dissolves and becomes the p-type gallium nitride. And for the fabrication of blue LEDs, there are another important thing, that is the indium gallium nitride. The band gap of gallium nitride is in the UV regions. So in order to realize the efficient blue LEDs, we need to reduce the band gap in the blue region. Okay? So we started the indium gallium nitride growth from 1986, but we only grew indium gallium nitride with the indium content of only 1.7%. In order to realize blue LEDs, we need at least 15% of indium. Okay? The reason is quite simple. Dr. Matsuoka, at that time, NTT, realized the first high indium content indium gallium nitride in 1989. The reason why we couldn't grow indium gallium nitride and they could grow indium gallium nitride is the difference of carrier gas. We used hydrogen as a carrier gas, but hydrogen attacks the indium gallium nitride, so it easily decomposes. So we have to use the inert gas, like nitrogen or argon. And the Professor Matsuoka's team used the nitrogen as a carrier gas and then realized the indium gallium nitride. But his indium gallium nitride quality is not so good. So it emits blue light at low temperature, but at room temperature, it does not emit blue light. But in 1992, Professor Nakamura's team, the Nichia Corporation, realized the room temperature blueluminescence. And then finally, the Professor Nakamura's team realized the first indium gallium nitride blue LEDs in 1993. That's the whole history of the blue LEDs. And in 1995, they also developed quantum well-based blue LEDs, which is become the standard technology of today's blue LEDs. Okay. So when I was a student, I only considered or I only imagined the application to displays, but this is the blue LEDs, okay? And by combining these blue LEDs with the phosphor materials, we can easily realize the white LEDs like this. This technology was developed by the Nichia Corporation. The one engineers developed these technologies, by which the applications of blue LEDs expanded enormously. Then I'd like to explain how this white LED technology contribute to the energy savings, especially in Japan. There were 48 reactors in Japan, but all the reactors stopped operation. So before the year 2011, this year the Great East Japan earthquake occurred. Before the year 2011, about 30% of the electricity was generated by the nuclear reactor, which is quite similar in Finland. But after the 2011, all the reactors stopped operation. So we have to find another way of adapting this 30% electricity. This is the US Department of Energy forecast of LED lighting market. In case of United States, by year 2030, market share of LED lightings in the general lighting exceeds 70% by year 2030, and by which they can save energy of 7%. Okay. But in case of Japan, the penetration of LED lightings is much faster. In case of Japan, by year 2020, over 70% of general lighting is replaced to LEDs. So by which we can save about 7% of electricity by year 2020. Okay. More importantly, we can supply the very easy lighting system to the people living in the area at which the people cannot access to the electricities. Okay? For example, the Minister of Education in Mongol visited us, and he said that in case of Mongol, more than 80% of the people are still living without house, so moving around. So they need the lighting system, but by the emergence of lighting system based on LEDs, they can provide the lighting, especially for the children. So the children in Mongol can read the books and study at night. Of course, it is very useful for the African people and the South American people. Okay. Finally, I'd like to send a message to the young researchers or young people. Okay. When we realized low temperature buffer, I was 24 years old. And when we realized the P-type gallium nitride, I was 28 years old. Yeah, of course, I was so lucky to be in the Professor Akasaki's, the excellent professor's laboratory. But if we consider the funding situation at that time, maybe young people, the research condition is much better than the previous or our age. So I hope that young people try much challenging task or the difficult task. So by which the young people can develop a new world or better life by themselves. Okay. That's all. Thank you so much for your kind attention.
Thank you. Thank you very much, Professor Amano. So now there's, of course, time for questions. So be brave. Hands up. Okay.
In Professor Nakamura's one of the opening papers from 1986, he's referring to you, to Professor Akasaki and to you 4 times. Did you know him already earlier, or was he just reading literature very carefully to find out where the development is going?
The Professor Nakamura?
Yes.
Yeah, he started the nitride research from 1989.
Right.
So we did not know him.
You didn't know each other?
No, never until the 1989 or 1990. He started the presentation at the conference. So we knew him from 1990s.
Right.
Yeah.
Okay.
Could you briefly explain how exactly LEDs work for those of us that aren't perhaps too familiar with it?
The question is how precisely the LEDs can operate, or
Yes. How does an LED work?
how?
Where does the light come
very
from?
difficult. Okay. Can you explain by the recombination of electron holes or?
Come again?
Yeah. From from the quantum mechanics point of view, it's energy transfer from the electrons to the photons. Okay. The electrons at higher energies lose energies by recombining with the holes, the positively charged holes. Then this energy automatically transfer to the photons. It's called the transition energy, or the energy level transitions from the higher energy level to lower energy levels. Maybe it is difficult to explain.
Thank you for your very interesting lecture. I would like to ask that, what do you wish to achieve next? Do you still have a dream? What do you want to do next?
Oh, the next dream. Okay. Our next dream is, there are several subjects or problems that we have to solve, in the global vision. For example, the food, or the environment, or energies, among which we are now concentrating on solving the energy problems. By using LEDs, we can save 7% of energies in Japan. But there are another way of solving the energy problems by realizing a higher efficiency system. For example, if we realize the high power transistors based on the same materials, the gallium nitride, we can save energy over 9%. So adding the 7% and 9%, it's 16%. So it's about half of electricity generated by nuclear power plants. That's our second dreams.
Hi.
How do you see the research situation with LEDs? Is there something yet to be discovered, or are we at the peak?
Could you?
How do you see the research situation with LEDs? Is there something yet to be discovered, or are we at the peak?
Today or?
Today.
Oh, today, okay. Today. Yeah, well, one of the most exciting target for us for LEDs is to develop UV or deep UV LEDs, much higher energy photon LEDs. By realizing UV or deep UV LEDs, we can supply very convenient water purification system or air purification system. So one of our next target for LEDs is to develop deep UV LEDs. And also we are interested in fabricating or different types of structure like three-dimensional LEDs by which we can reduce the cost of LEDs. That's another target. Efficiency. Yeah, efficiency. Oh. The efficiency of blue LEDs in terms of quantum efficiency is close to 80%. But wall plug efficiency is a little bit lower. And for deep UV LEDs, the efficiency is still low. It's smaller than 20%. And also, for three-dimensional LED system, the efficiency is limited to below. And we, for both cases, we knew why the efficiency is so low, but we couldn't find a way of improving the efficiency.
Yeah, that's a very nice, successful story, and well, after this success and that you have also this interview, and okay, sorry, Finland has no royal family to receive you, but do you still manage to actually have time to do research, and how does that impact on your research
That's
team?
a very important point. I never manage the research of my group. Okay. For me, the most important things to continue the research is I could proceed by myself. I consider the next experiment by myself without any suggestion of the professors. Okay? So I succeeded this style to the younger generation. The students consider by themselves, and they can do research by themselves. So I do not manage the research. Okay.
Very good. Actually, I have a question.
Oh?
Yeah. What is the main factor limiting the price
Of
solid-state lighting? No, white light.
Oh, white light.
Yeah.
Yeah, to tell the truth, the most serious factor is not the chip, but the packaging. Yeah, the energy density of LEDs becomes higher and higher. So the thermal dissipation becomes more and more serious. So we have to use the good ceramics for thermal dissipation, but it is very, very expensive. So the cost of the packaging is more than 3 times higher than the chip itself. Chip itself is not so expensive. The problem is the packaging.
So there's some work to do there.
Yeah.
Hi, so you seem really enthusiastic about the future of LED for saving energy. Do you think the supply in gallium and will be enough, for example, for developing fully this technology?
The gallium.
Yeah, the supply of the raw material, will it be
I
enough in
see.
the long term?
That's a very important point. Previously, the lack of indium is serious because we have to use the indium tin oxide as the transparent electrode, and the volume is very large. But today, the problem of the indium deficiency is solved because previously the people in the mountain does not recognize the importance of indium, so they abandon or get off every indium. But now, when we get the indium from the what should I say? We found that the amount of indium is sufficient, and also the amount of gallium is sufficient. If we recycle the gallium from the old LEDs or old systems, so at least for application to LEDs, the amount of gallium is not the problem.
Hi, can I ask please a personal question? How did you come up with the idea to become a scientist? Why did you decide to become a scientist? To do...
become a scientist?
Yeah.
Oh. I myself do not recognize that I'm a scientist. Yeah, I continued the research because it is so interesting. Now I became the professor, but I never tried to become a scientist, or I never tried to become a professor. When I continue the research, I automatically become a professor. I never intended to do that. Okay.
Thank you for your answer.
Thank you. Professor by accident.
Yeah, by accident, you're right.
That is good. So, okay, let's close the public discussion for now and thank Professor Amano once more. Okay.